Hello my dear friends, today I am come back with a new topic. The topic of today's presentation is design and analysis of double gate junctionless TFET for gas sensing application. So let's start. Before we will start, I will make a request on you. If you like my video, please subscribe my channel and circulate these video to your friends also so that they get benefit from this video. Let's start. The first question is comes out, what is junctionless transistor? First, we will talk about junctionless transistor FET. After that, we will talk about junctionless tunnel field effect transistor. So let's start from the junctionless field effect transistor. A multiple gate MOSFET such as double gate MOSFET, FinFET and gate all around structures provides better electrostatic control because more than one gate is controlling the channel. Despite having better show channel effects, the formation of such a sharp junction of an ultra-scaled device is quite challenging. One thing comes out from here. In case of doped structure, we have to require a sharp junction. If we will talk about the fabrication, then it's a quite challenging task to obtain sharp junction for an ultra-scale device. A junctionless transistor recently emerged as a promising device having characteristics similar to conventional MOSFET and is uniformly doped device with either N plus for N-GLT and P plus for P-GLT, P-type GLT. Therefore, the fabrication steps are simpler as compared to conventional MOSFET. It can be seen in the figure that. Then the figure A is junctionless FET and figure B is doped FET. It can be seen in the figure that in a junctionless transistor, the entire section, the entire substrate is silicon film doped with N plus impurity or N-type GLT. N plus doping is almost 10 raised to power 19 per centimeter cube. But in case of doped semiconductor, the source having the different doping about 20 and the channel having the different doping around 15, 16 and the drain having doping around 1E19 or 5E18 per centimeter cube. Due to the work function difference between the P plus gate and the N plus thin silicon film, the N-type GLT device is fully depleted and there is a barrier between source and channel in off state. Now the question comes out, in case of GLT, there is a no barrier, no depletion there, no junction is there. So how the junction will be created? The junction will be created by using different work function. We are using a different work function at the gate terminal. In case of junctionless transistor, the gate work function having high value. The high value of gate work function will deplete the N plus top device into P plus in the channel area by using a work function having a value around 5 electron volt. Is required to change the N plus top channel layer into a P plus. Due to the work function difference between the P plus gate and the N plus thin silicon film, the N-type GLT is fully depleted and a barrier is created between the source and the channel junction in off state. By increasing gate bias, when you provide the gate voltage at the gate terminal, a channel is formed within the bulk and the conduction is take place. Initially, by applying the work function, the N plus layer is fully depleted and transformed into P plus. When you applying the gate voltage, then a channel is created and the conduction will take place between the source channel and drain terminal in case of junctionless transistor. Next, we will talk about junctionless tunnel field effect transistor. We know that the tunnel field effect transistor is different from the FET. In case of FET, drain and the source having the same doping. but in case of TFET, force having the different doping as compared to drain terminal. So let's start. The junctionless tunnel field effect transistor consists of silicon channel heavily N-type doped junctionless field effect transistor, which uses two different metal work function to behave like a tunnel field effect transistor. In case of TFET, we are using two different work function, one at the gain terminal and one at the source terminal. In case of FET, we didn't apply any work function at the source terminal because N-type is required in the FET. But in case of tunnel field effect transistor, in case of N-type transistor, we have to require P plus at the source terminal. So that we have to apply work function at the source terminal also. The P plus source region is introduced by applying matter work function on highly doped N-type silicon substrate. To convert or transform source region, which is already N-type, into P plus, we have to apply a higher work function. A work function around 5.93 electron volt is provided at the source terminal to transform N plus layer into P plus source region. Next point. It does not have any metallurgical junction. We know that in case of junctionless device, there is no junction at the source channel and drain channel interface. Since this device has no concentration gradient, if we are not using the doping profile, so that there is no concentration gradient in the lateral direction of the conduction layer. It does not have any PN junction. It should be simpler to fabricate, have better electrical properties, and less variability than MOSFET. Next point. Junctionless tunnel field effect transistor is created by picking suitable metal electrode work function of source, which helps in creating a desired P plus source region in a heavily doped N-type silicon body. The concentration of the substrate in case of junctionless transistor is 10 raised to power 19 per centimeter cube. Due to absence of the sharp doping gradient, it has better scalability and less source channel effects. Although the subthreshold slope of the junctionless tunnel field effect transistor is below 60 mV per decade at room temperature, it has low on current and gives poor I-on-I-off ratio. By using different techniques such as strained silicon, dual material gate technique, we can improve the on current. Because device is junctionless, we can reduce the size of the semiconductor device. We can reduce the length of the gate channel in case of junctionless transistor as compared to conventional transistor. Next, we will talk about junctionless vertical tunnel field effect transistor gain sensor. In the last video, we had already talked about why vertical TFET is now used in most of the application. If you did not listen my last video, please go for that. The title of my last video is Dual Source Vertical TFET, in which I have explained that why vertical TFET is so preferred nowadays. In this present study, junctionless vertical tunnel field effect transistor with catalytic metal as gate contact is proposed for gas sensing application. The vertical double-side gate architecture provides better gate controllability over conventional TFET for band-to-band tunneling mechanism. An architecture of N-channel junctionless vertical tunnel field effect transistor with palladium as gate metal is analyzed for hydrogen sensing, hydrogen gas sensing, while cobalt and molybdenum metal as gate contact are analyzed for ammonia gas sensing. P plus pocket are created near the source region by using work function value befitting the aforementioned catalytic metal. Nowadays, we preferred vertical TFET gas sensor. There are a number of advantages of using vertical TFET as a gas sensor. In the next slide, we will discuss about that. For using junctionless vertical TFET as GaN sensor, we used catalytic metal at the gate terminal, which can absorb the GaNs or sense the GaNs and recognize the GaNs, which can helpful in the GaN sensing application. Palladium metal used for the hydrogen gas sensing, and cobalt and the molybdenum metal used as ammonia gas sensing. As the metal work function at the gate changes with the presence of gas on it, there is a change in I off, I on and threshold voltage, which can be taken as sensitivity parameters for sensing the gas molecule. In the last slide, we had talked about the catalytic metal are used as a gate metal. As the metal work function of the gate is changing by the gas pressure on it, its I-off and ion current and threshold voltage are changing, which can be used as a sensitivity parameters for GaN sensor device. These GaN sensors mainly work as transducer device that detect the presence of different GaNs such as S2 GaNs, measure its concentration and produce an electrical signal that is further calibrated with the magnitude of S2 gas concentration. Junctionless vertical TFET work as a transducer device which can detect the gas, measure its concentration and produce a corresponding electrical signal on that, which can helpful to find out the concentration of the gas molecule. Out of various GaN sensors such as catalytic sensors, semiconductor sensors, electrochemical sensors, and infrared sensors, semiconductor sensors has number of advantages and have numerous benefits which can be used for an extensive range of gases including toxic, combustible, and etc. Further, the low cost, high sensitivity, stability, fast response time, wide operation temperature range, and reliability make it highly applicative for detection of variety of gases. The successful utilization of junctionless vertical TFET in GaN sensors may open a new door for the development of novel nanostructure GaN sensing devices. Hello my dear friends, I have mentioned everything in my slides. If you did not understand my voice properly, you can read out these slides. You will get all the information you have required to understand this gas sensor device. Go to the next slide. First, we will talk about S2 GaN sensor, how it works. Palladium has a very high selectivity towards S2 GaNs. That's why we are used PD as a gate metal, as a catalytic metal in FET device. PD based GaN sensor rely on the fact that after absorption of the S2 GaNs, a chemical species called palladium hydride is formed, which has a comparatively high electrical resistance. When S2 GaNs are fired on the gate metal, then a palladium hydride oxide is formed, which has a more high electrical resistance power as compared to SiO2 gas. Second point, apart from high selectivity, out of several catalytic metals, the sensitivity of PD for hydrogen is highly appreciable because of the sites located at PD-SiO2 interface in case of Morse architecture and TFET architecture, along with the surface reaction participating in the catalytic reaction. Only in case of FET or TFET devices, you will obtain PD-SiO2, palladium hydride oxide at the interface of gate channel. It is also reported that at room temperature and atmospheric pressure, PD can absorb up to 900 times its volume of gas. When S2 GaNs interact with the PD surface, the S2 molecule dissociate on the surface of the metal to form atomic hydrogen, and some of the dissociated atom, hydrogen atom, diffuse through the PD surface. The probability of dissociation of S2 on PD is almost unity, or S2 dissociate very meritoriously on PD. When S2 gains fire on the gate metal, or we can say that when the S2 gains interact with the PD surface, the S2 molecule are dissociate, interacting with the metal surface. Then the dissociated atom diffuse through the PD surface. Some of the atom are stick at the metal, and the some of the metal are diffuse through the PD surface. The probability of the dissociation of the S2 atom is almost unity, and it can easily dissociate after interacting with the PD metal surface, and most of the atom are diffused into the PD metal and reach to the SiO2 surface and makes PdSiO2 palladium hydride oxide at the channel surface. Within few nanoseconds, the diffused hydrogen atom reaches to the interface of PD and SiO2, or the hydrogen atom gets absorbed at the SiO2 PD interface. The hydrogen atom reaching the metal insulator interface gets polarized and forms surface dipole layer. Those atoms get diffused into the PD metal surface. They will get polarized and forms dipole layer at the interface. This dipole layer in turn modulate the work function. The dipole layer are formed at the PD SiO2 interface, and the function of this layer is to modulate the gate work function. It also modulates the conductivity of the device also, and thus affect the device electrical properties. The high sensitivity of the PD for S2 is mainly attributed to the great polarization of hydrogen atom at the PD SiO2 interface, rather than the large diffusion of hydrogen atom through PD. The reason behind the high sensitivity of the palladium atom is mainly due to the great polarization of hydrogen atom at the PD-SiO2 interface. This is the basic principle to understand how the hydrogen gains junctionless vertical TFET gain sensor work. The entire analysis has been performed at room temperature. A lot of work in the field of the semiconductor gain sensor has been carried out with MOSFETs, but there is a now need to investigate the vertical TFET as a gain sensor. This one I am doing that, as vertical TFET is highly suitable for low power digital CMOS applications. The novel properties of the vertical TFET, such as low leakage current, lower subthreshold swing less than 60 mV per decade, immunity against short channel effects, makes it an outstanding candidate for low power devices in the semiconductor industry. This one is the proposed device design. Figure 1 represents the two-dimensional schematics of the proposed junctionless vertical TFET. The conventional gate oxide is replaced by the SiO2 HFO2 stacked gate oxide integrated bilaterally across the channel. The purpose of using the gate stacking, it will help in the fabrication of the device. For making the device junctionless, N-type doping of 1 into 10 raised to power 19 per centimeter cube is used as a silicon body with channel length of 50 nanometer and the channel thickness of 10 nanometer. Platinum metal contact with work function of 5.93 electron volt have been used for source electrode to create P plus pocket. I have already told you about that. In case of junctionless TFET, you have to apply a higher work function at the source end to transform or convert N plus layer into P plus source region. Highly reactive catalytic metal cobalt and molybdenum. Cobalt metal work function 5 electron volt and the molybdenum work function is around 4.4 to 4.95 electron volt. Have been used as a gate metal for ammonia gas sensing, while radium metal work function around 5.2 to 5.5 electron volt has been used for hydrogen gas sensing due to their high reactivity towards the respective gases. My dear friend, let's go to the code. Every code is start at the go atlas command. Mesh base.multipoint. It is a multiplying factor of the meshing. The device length is start from the 0. X meshing is start from the 0 up to the 50 nanometer with the different spacing. At 0 the spacing is 0.005. It's moved to 0.001, 0.005, 0.001. You can note down every quantity very carefully to run this code in your computer. And the next is Y meshing is start from the 0 and end at the 150 nanometer with the different spacing. The variation in the X meshing spacing is large as compared to Y meshing spacing. You can note down that at the junction we are using the fine doping and other part we are using the coarse doping. Next is the reason. Reason number 1 is for the SiO2. X maximum 0.050. X minimum is not mentioned in the code. This means you have to understood that the minimum value of X is taken as X minimum. Same is for the Y maximum is 0.150 and the Y minimum is the minimum value of Y, it is 0. And the reason number 2 is 3, 4, 5. Reason is used for the silicon material. Reason number 6, 7 is used for the oxide layer, SiO2 layer. And the reason number 8 and 9 is used for the HFO2 layer. And its positional parameter for every reason is mentioned in the code. Next is the electrode reason. Electrode name is drain, gate, gate 1, gate 2. We are using the triple gate method. That's why we are using the gate 1 and gate 2. We have taken double gate so that we have used left side gate 1, gate 2 and the right side gate 1, gate 2. Next is the source electrode. I had mentioned every metal electrode with their positional parameter. Please note down every step very carefully. Next is the uniform doping of junction local. Next we have to apply the voltage, solve initial and the solve previous you can use, and the method Newton and trap. We had mentioned the maximum trap 10. V source is 0 volt and V gate is 0 volt when the device is in off state. When the device is in off state, we are applying the drain voltage from 0 to 1 volt. To make the device on, you have to apply the gate voltage. Next you have to create the log file and increase the gate voltage from 0 to 1 volt. Next we have to observe or see the output waveform with the help of Tony plot command. Next I will define the various commands: output balance band, trap charges, surface potential, electron density, electron mobility. You have to mention this code to find out surface potential, electron density from the structure file. Next you have to save the structure file and you can observe with the help of the Tony plot command. And the last one is quit. When you run this code, I'm running this code. When you run this code, you will get the two files. One file for the structure and one file for the log. This is the structure file. Triple metal gate per function. And this is the HFO2 layer. This is the SiO2 layer for gate stacking. We have divided the source, drain and channel region, but we are applying the uniform doping. Approximate 10 raised to power 19 per centimeter cube. I will show you log file. This is the log file. If you want to check the current in the log value, click on the log. OK. The off current is approximately 10 raised to power minus 16 and the on current is very high, approximate 10 raised to power minus 4. But the substructure slope is high. That look like. If we are changing the work function, then the substructure slope of the graph will change. Let's move to the slides. Next is junctionless vertical tunnel fill effect transistor GaN sensor working principle. GaN sensor work on the principle of conversion of concentrations of various gaseous molecules into standard electrical signal by using specific physical and chemical effects. When gas molecules of harmful gases like hydrogen and ammonia react with the catalytic metal surface at the gate contact, it brings in a change in the gate work function. We have already in the last slide in the H2 GaNs, I have explained how the gas molecule of the hydrogen atom affected the gate metal work function and its conductivity. Equation 1, this one, represents work function variability on account of absorption of pernicious gaseous molecules. Delta phi m is the change in the catalytic metal gate work function induced by the gas molecule reaction at the metal surface. Delta phi m depends upon the gate metal and the gas to be detected and is given by. The formula of delta phi m is this one. This is the continuous work function and minus this factor. This factor will depend how the gate work function modulate, in which R denote the gas constant, T is the absolute temperature, F denote the Faraday's constant and P denote the partial pressure of the gas. The relational dependency of partial pressure of a gas on its concentrations can be utilized to calibrate the device in terms of mole fraction of the gas in air. TFET shows 1.4 into VTH standard deviation than conventional MOSFET. TFET is more sensible device than MOSFET, and most of their attributes are evaluated by work function value of gate metals near the source where band-to-band tunneling mechanism take place. Thus, work function variation cause change in the threshold voltage and flatband voltage, which further alters the drain current I on and I off and its ratio. Next slide. The FET is used as a transducer, which transforms the shift of work function at the surface of the sensitive film catalytic metal into a corresponding electrical signal, a change in the drain source current. Simply, FET is used as a transducer which can transform the variation in the gate metal work function into the electrical signal, which results in the change in the drain current and the various factor also like threshold voltage and ion I-off ratio and sub-threshold swing of the device. Reaction of gas molecules at the catalytic metal gate surface results in the change in the work function of the gate metal, which further cause change in the flatband voltage due to the additional band bending. Flatband voltage change results in the shift in the surface potential, threshold voltage, and the drain current of the device. Thus, by monitoring the change in the threshold voltage, I-off, ion, and subthreshold slope, it is possible to detect the presence of the gas molecules. For example, oxygen, hydrogen, ammonia, and other hydrocarbons using suitable catalytic metal gate work function. The dependency of the flatband voltage VFB on work function is represented through equation 2. How the change in the flatband voltage vary with the change in the gate metal work function. VFB is equal to phi m minus phi s plus minus phi m. where phi m denote the metal gate work function. We know that delta phi m denote the gate metal work function variation. Delta phi m is equal to the metal gate work function without gas molecule minus gate work function with gas molecule, and phi s denote the work function of silicon given by the equation 3. Simply phi s denote the work function of the silicon material. We know that the work function of the silicon material is equal to Eg by 2 electron band gap plus electron affinity minus Q delta Fp for n channel device. The variation in threshold voltage affect the subthreshold current of the device, which change the I of current represented by the equation 4. The equation of the subthreshold current is equal to this one, I naught E, this one factor VGS minus VTS divided by eta VT into me 1 minus e की power minus VDS by VT, in which I naught represent this one, W by L, mobility of the electron, oxide, thermal voltage here e की power minus 1.8, and the VT, thermal voltage. VGS, VDS and VT are the gate to source, drain to source and the thermal voltage of the device respectively. L and W denote the length and the effective width of the transistor respectively. Qx denotes the oxide capacitance of the gate, eta denotes the coefficient of the subthreshold swing, and mu n denotes the electron mobility. Now we will talk about the result. Figure A, B and C. This one. A, B and C represent the effect of variation of 50 milli electron volt, 100 milli electron volt, 150 milli electron volt and 200 milli electron volt in work function on the drain current for cobalt, molybdenum and the palladium respectively. As can be seen in the figure that the I of current is changed exponentially when the work function is changed in milli electron volt, and it is clearly show that the effect of the gas molecule is much higher on I of as compared to I on. Thus, subthreshold region offers much higher sensitivity along with low power operation, thus providing low cost gas sensor device. In the junctionless device, if you change the gate work function, then its off current will be changed. But in the doped and the charged plasma device, if you are changing the gate work function, the most effect of the changing the gate work function on the on current. But in case of junctionless device, by changing the gate work function, produce the more effect on the off current of the device. With increase in work function, we can note down in the figure, with increase in the work function, the steepness of the energy band diagram of source channel interface decreases, leading to a reduction in the tunneling probability to the conduction band. By reduction in the tunneling probability, the off current start decreasing. We can note down that in the figure that if you are increasing the gate work function, the tunneling probability is reduced in the off state, which result in the decrease in the off current of the device. The reason behind is that the duality of a high enough potential barrier is in the prevention of tunneled electron from overwhelming it, or allowing only those with adequate energy to flow towards the drain directly from the channel. Due to the reduction in the tunneling probability and increase in the barrier at the source channel interface, only the high energy electron can cross from the source to the channel region. This will result in the reduction in the off current of the device when the device is in off state. Thus, only those electrons having high enough energy become part of the band-to-band tunneling mechanism in the off state. This causes the exponential decrement in the off current with increasing work function. The on state current is not much influenced by the work function variation. You can note down in the figure. The variation in the on current is very less as compared to the variation in the off current of the device. This is the sensitivity comparison. Sensitivity calculation of the junctionless vertical TFET based gas sensor using cobalt first table for the cobalt gate electrode. This one. Second table for the molybdenum gate electrode and the third table is for the palladium gate electrode. And the third one is used for the hydrogen gas sensing, and the above two metals are used for the ammonia gas sensing. From the table, you can note it down that without gas, we will get the current up in the 1.83 into 10 raised to the minus 10. If you are applying the gas molecule at the gate electrode, the current of the device is decreasing. You can note down in the figure. Both for the cobalt and the molybdenum electrode. When without gas, you are getting the high of current. When you are applying the gas molecule at the gate metal electrode, then the off current start reducing. It will reduce up to the 10 raised to power minus 14 in case of cobalt metal electrode and 10 raised to power minus 11 for the molybdenum gate electrode. But in case of the palladium gate electrode, you are getting the off current around 10 raised to power minus 14, very high without gas molecule. If you are applying the gas molecule at the gate electrode, the off current is reducing very fast. It will reduce up to the 10 raised to power minus 16 ampere per micrometer of current of the device. You can note down that there is no change, approximately no change in the on current, either in the case of cobalt, molybdenum or palladium electrode. By reducing the off current, we are increasing the I-off ratio. This means if we are applying the gas molecule at the gate electrode, the ion-I ratio is increasing. It will be increased up to the 10 raised to power 6 to 10 raised to power 10 in case of cobalt electrode, and in case of molybdenum electrode, it will increase up to the 10 raised to power 4 to 10 raised to power 7, and in the case of the palladium gate electrode, the off current is increased. The ion-I ratio is increasing up to 10 raised to power 10 to 10 raised to power 12. Next is the last one is the future scope. Further optimization may be done in terms of gate engineering and the channel related parameters to implement a cost effective low power gas sensor with less on chip area, studying the device behavior in the subthreshold region, provide scope for enhanced sensitivity of the device gas sensor. Second, the vertical architecture with increased gate controllability and the absence of the sharp doping gradient makes junctionless vertical TFET a promising candidate for future research on gas sensing device. My dear friends, this is end for today. You can do the further optimization of my gas sensor device on the basis of the gate engineering, on the basis of the channel related parameter, and on the basis of their sensitivity and selectivity also. If you want to do the extension of my work, please contact to me. I will guide you. Thanks for watching my video. Please like and subscribe my channel. Thanks a lot.